Okay. So you hear me, I'm sure.
Sure.
Yeah. And you see the red one. Okay, I tried to make a modest title, and this was the result of my thinking. So the Internet of everything, you can think about everything, it's all in the Internet. And what I will talk about is in cooperation with Peter Fettke, who is sitting over there, and who will give another talk in the afternoon. Okay. So I changed my first slide a little bit, because yesterday we had this talk of Rick Katzmann, who spoke about challenges in architecting with 4.0 systems. I think most of you will remember it was a brilliant talk, and I think we all agreed that about what he said, that there is an enormous design depth in today's software. I think so far we agree with him completely. And what else he said is, how can we analyze this kind of software systems? And maybe now we don't agree again about my answer to this question, because my answer is, don't do it. It's a stupid idea to analyze software systems. Instead, we should start the system design with modeling, which involves the real problem. We should start from the real problem and not from the software idea, as well as from the solution. And for instance, the problem would be make a company's administration more efficient. That is a problem, and not a database problem. So these are the real world problems, and we should start with them. And then we should ask, how can we analyze models, and not make a lousy software and then try to analyze the software. So this is the wrong kind of starting point. Okay, and then generate software from models, and then the software should be correct by construction. So the idea, and of course, I know what you all think. I know it precisely. You all think that has been attempted several times in the 1960s, 60s, 70s, 80s, 90s. It was tried several times and it always failed. And that is true so far, but try harder and especially use the right modeling concept. So I think the fundamental problem with this approach is that we don't.
Closer? Closer to your mouth?
Closer?
Thank you.
Okay. The fundamental problem with this approach is that so far we didn't have the right modeling concept. And the question is, so which modeling concept should we use? And that is what I will speak about, and what Peter will show you an example about. Okay. Well, let's start how we model the Internet of everything. I think all engineering, all serious engineering fields start with models. Architects, civil engineers, everybody starts with models. All the computer science starts with product. So you have an idea in your mind and then you write code. And this is not a serious way to make engineering. So we should start with the models and not with an intuition. The art of computer programming was one of the famous, but very famous book by Don Knuth in the end of 1960s, beginning of 1970s. But it's a completely wrong way to start. We are not artists, or we should not be artists. We should be engineers. And that means we should start with models and discuss the models and show the models are correct. And then derive the product that we want from the models. Okay, so the usual way, first to write a lousy software and then to repair it. That's a classical way to do it. And my question is, can you imagine this is a factory for car production, and after the cars have been produced, they go to a workshop and they repair the freshly built cars. And the workshop is bigger than the factory. Nobody would build cars like this, but software is produced like this. And instead you should make a model. For instance, this is a model of a famous building, and from the model you derive the product that is, in our case, the software by construction, and it is correct because beforehand we have proven that the model was correct.
But the product looks different from the model.
Yes, of course it is. Of course it is. But it is derived from the model. So modeling informatics should be about a change of the perspective. It's a fundamental change that we suggest. You should not start with thinking about computers at all in the beginning. You should start thinking about the problem you want to solve. And especially in business informatics, and Peter comes from business informatics, where you have to model a lot of components that are never intended to be implemented, but that are intended to be executed by person. So then it makes anyway no sense to start with the tiny parts that are made by computers. Okay. Now the question is, how can we start with such a modeling technique that is so generic and so general that it applies to everything, so everything, the internet of everything. And I start with three postulates. A postulate is something we should all agree about, and this is really true for any kind of a model. And so a comprehensive model of the internet, for instance, is somehow structured. The internet is not a monolithic something. It has any kind of a structure. I do not yet speak about which structure it is. It may be differently structured according to different interests, but it is never monolithic. We need some kind of structural principles in this context. Does anybody not agree? Okay, everybody agrees. That's what I expected. The second point is the comprehensive model of the internet includes data and real-life items. So we do not only speak about data in this context, but also about, say, invoices. We have to pay an invoice. So an invoice is not a data, because if you don't pay the invoice, you go to prison at the end. And if you treat data in some way, you never go to prison, because you treated the data not nicely.
But why do you call this static? Statics.
Statics, not statistics. So these are some static aspects. And the third postulate is that if there is some dynamics in this game, then dynamics is always locally. That is, say, if you have a computer in the internet and you press a key, it makes no sense to say, aha, there was the original state of the internet, and pressing the key gives you a new state of the internet. So to speak about the global state of the internet makes no sense. There are some kind of states, of course we need some kind of states, but not global states. You don't update the internet suddenly, so make a jump and there's a new state of the global internet. Instead you have something locally occurring, and then it will have some effect in the internet. Okay, so these are the three postulates with which we start.
In building architecture, the statics is a part of the architecture. So are the postulates redundant?
Not in the building, what do you mean in the building architecture?
If you want to build a house, the architect does a plan, and it goes to a statistic person, to a static person in order to ensure that the architect of the house is
no, not this kind of statics. No, it's
then I don't get
things that don't change for a while.
Yeah, but then static and dynamics is a contradiction.
Is what?
A contradiction for the...
No, you need data, you need things that do not change, and then you must describe things that change. There are things that do not change. For instance, the natural numbers. They never change, and you use the natural numbers, and you can say this is a static aspect of the world which does not change.
Okay.
Still you use them. And the aspect of dynamics means...
Yeah,
okay.
That's what I said.
Okay, so these are the three ingredients in the modeling world, and if you have the internet of everything, you have the three columns, and from them you have to build the model. Okay, now let's go more to the details. what can we say in a very general way about architecture, and then what can we say about static aspects, and then about dynamic aspects. These are the three aspects that I will talk about. Okay, so let's look at what literature offers. There are modeling techniques already, and they have modules and they have parallel composition, and I've written some here. There are business process modeling techniques, there are architectural languages that speak about modeling. I don't go into the details. My point is all of them focus implementability. They all focus starting with the computer and not with the real problem. And that's what we need. I said it already, we need a fundamental technique that is more general, more abstract, more simple. That is very important. And focusing or starting with the real world problems and not with computers. And I give you now a very quick example of how we would do this, so then to show you the notion of a component and the notion of composition. So you make some internet shopping, there are orderings of customers, and eventually the customers will accept the overall delivery. Now you look inside this, there are customer sends an order, gets a message, gets deliveries. There's a business that accepts purchase orders, sends messages, etc., does something else. And the point is, this is the way they compose. Very simple. So if they have two, say, ports with the same labeling, then we do them. So now we have already constructed customers with business. Now there will be freight forwarder, and as a business can send something to freight forwarder, we compose them this way. And now comes a very important aspect. We have delivery certain here and delivery certain here, and that composes also. Okay? And now we've already the customers freight, business freight forwarders, etc. Here we have the supplier for the business that we write this way. And then we can look inside the business and say the business is order management, inventory management, the warehouse, and thus you can get an arbitrarily large system. You can zoom in any kind of detail, you can compose any new components, and until you have the entire data. Okay. So technically, I make this very quickly to show the generality. You just have a graph, any kind of a graph, with two sets of distinguished labels. One is called star G and P star, and that is now the point that we have seen already. The interface is distinguished in the left part and the right part. Very important, very fundamental, and with this you can cover very many things. So left and right interface, and composition means you glue the elements of the right interface of the left component with the left interface of the right component, and you see two of those components. You see the B occurs here. So this is the composition, and from the composed system, this is the left interface and this is the right interface. I'll give you another example. And there's a fundamental, I forgot, there's a fundamental theory which you always implicitly assume, and many of literature implicitly assumes it without ever having proven it, namely that we don't need brackets. We can compose them without writing brackets because it's associative. Without this property, it would all have no sense. So we ask why is left and right so important? Well, input and output, customer, supplier, etc. Because you find all these pairs of things anyway in the world. And to give you another example, there's a typical module that is called Frank, and he has left and right interface, A B. And but we laugh a little too. And this is me, and Graf has, Frank has learned that I have a Porsche and I want to sell my Porsche. And he tries to be clever and he offers me 30,000 euros for my Porsche. He doesn't know my Porsche. But he offers me 30,000 because he assumes that Bernard will pay him for 50,000. Okay, so we compose this way, and then he talks to Bernard, and Bernard composes with him. But Frank did not recognize that also the C's down here compose. Of course, so now we compose me and Frank and Bernard, and this is the result. And then Bernard asked me if he could have a look at my Porsche, which Frank did not look at. So I showed Bernard my Porsche, and this is my Porsche, and Frank has paid me 30,000 for this Porsche. Okay. I have got the 30,000, I don't give them back. So now you have understood how composition works. Okay. So this kind of composition is universal. What does it mean? It means for any graph, the nodes can be made to modules, and then you can compose them. As an example here, this node B can be made to a module, for instance, this one. This A is left, C and D is right, and this is left, this is right. And each graph can be composed from this kind of modules. So it is this composition operator is general enough. You can do everything you want. In this case, it could write A, B, C, D. You could also make other modules and have another order. Okay. So you can ask, why do we want two interfaces? Why not only one? But if you try the same game with one interface, you will quickly understand it's not associative. And then you don't need it. Why not three? The above theorem has shown us two are enough, and three is only technically very intricate. So two is the right choice for everything, for any kind of composition. And now you can start to make a specific, defined kind of composition that you need in your complete system. So how can we manage complete a complex composition? Well, if you have any complex composition, I call it star, and in the star you can have whatever you wish. You want, for instance, change euros to rubles is not a good idea, to dollars or whatever. Then you just put inside an adapter, so another component, and this adapter, of course, has a left and right side very naturally. And in the adapter, you tell all the stories that you want to tell about the composition. So therefore, this simple composition is universal, because everything else you usually put into composition operators, you put them into the adapter component. Okay. How to manage refinement? I think you have seen this already by proper composition of final models. For instance, here you can see...
a little bit slow. Did you prove that for each operator star, you can find an adapter?
What is each operator star?
Yeah, so what kind of stars can you realize by an adapter?
If the operator star, that it usually talks about data.
Yeah.
So you must define which class of data you are considering. And then you have a classical problem of computability. If your star is computable, you have a program or you have an automaton or whatever you can put inside the
Got it. Thank you.
So, yeah. Okay, so refinement means just you have finer things and compose them, and the composed thing is, this is then a composition of three local components. Okay. So, how manage really big systems, and that was the work of Internet of Everything. So keep everything local. The whole theory is made such that everything can remain, if you wish, inside the model you choose. The level of abstraction, composition is defined in two modules. Refinement is defined in one module, adapters, two modules. Data, but you may need few global names, very few, but that's all. And especially behavior should be without any global state. You should be able to speak about behavior of single modules without considering any, not considering the rest of the world. Okay, now comes statics, which was your point. Statically give me the data, real life items that we want to speak about, and operators on data and items. So what does it mean to make this as general as possible? Well, it's very simple how to organize all this. We learn from logic. We do not learn from informatics, but from predicate logics, they are much more smart. The predicate logicians are much smarter to speak about this than computer scientists are. And so we speak about structures and signatures. That is what logic does for long. And that's what informatics in some kind tries to also to cope, but does it in not a very clever way. And we do it consequently as logic suggests. And I just give you a glimpse of what the difference is between the structure and the signature, because many people confuse this because they are not taught the right way. So structure has some sets, ground sets, derived sets, constants and functions. And here are some sets that are taken from an example which I do not want to go into details, but very concrete sets, derived sets, concrete constants and concrete functions, which I do not go into details. Just you must know there are these kind of things. Here is another structure that is very similar but has different sets, different elements, different functions. And now I show you a signature. What does a signature say? Signature says there is a set of customers. Here we have concrete customers. There is a set of articles. Here we have small car, medium car, large car. The signature only says we have symbols for concrete sets, we have symbols for constant symbols, we have constant symbols, we have function symbols, then we have also variables and properties, but that does not belong to the signature. And from a signature, you can construct terms, what you usually do in mathematics anyway. You have terms like f of x or f of a and b of y. And this kind of, you have finitely many symbols, constant symbols and function symbols, and that gives you infinitely many terms. And now if you interpret in the structure the symbols, the finitely many symbols, then the meaning of the infinitely many terms is given for free. So that is what logic suggests, and that is what we should do, and that is what we do in our approach. So infinitely many terms in a structure that fits to the signature, each term has a meaning. Very important, and the meaning is given for free, but according to the inductive construction of terms. So long with inductive construction. I don't want to say anything else because we just say we adopt logic, we adopt what predicate logic does. But predicate logic then talks about properties for all x, blah blah, or they exist. This is what we do not do in the modeling explicitly, but the starting point with signatures and corresponding structures is exactly what logic does. So dynamics. Now it's important to point how can we speak about dynamics without speaking about global states. We have local states, and that means an event has local cause and effect. And usually an event affects only very few things. And well, this is an example which maybe is too big now. For instance, here we have Alice, she is an ordering customer, and she submits an order. Here she has submitted the order and she has a copy of that order. Then she gets a message, then she expects the delivery, and there are some deliveries. So what she ordered is delivered in 2 parcels, and then she collects it all and then she takes it. Be aware that this is a partial order. It looks not like a partial order, but it is partial order. There is no cycle at all, because this is one behavior of the system. I come back to this because this is an important aspect. Okay, here is a completely different thing. Here I want to say we have Alice, Bob, and Claire, so 3 clients, and they behave all according to the same schema. So now we say, aha, here is a variable k, and you have to instantiate the variable customer, and if you take Alice, then aha, here is other variable x, so she submits an order list, etc. So the structure is what we have seen before, but what we represent now is a behavior of 3 clients, and they can order any kind of thing. So x is a variable for article list. And here the variables are serious logical variables. They are not what computer science does, assignment statements to to stores. No, these are real variables, as in logic usually done. Okay, and now we have a system with three customers. Of course, sometimes we don't want to have three customers. We only want to say there is a set of customers, and then we want to instantiate the system. I think before, so the point that we have many systems that are structured in the same way, and we want to have an abstract schema to characterize them all. That's what we do here. And that's, of course, again taken from logic. That is not a new invention, it's only a new application of logic. Okay, so this is a schema for customers, and here is a notation saying the ordering customers, but if we just put here the symbol B, then it would say the ordering customers is a set of elements. That is not what we want to say. We want to say each element is an ordering customer. So we want, therefore we say here is the elements of B, and not the set B itself. Okay, now we put it all together. Now we have the three columns, and we put it.
So why do you rely on logic for the static aspects? Why don't you rely on logic for the dynamic, for example, using some temporal logic?
Well, I wanted to be modest and would have liked to say what we do is we breathe life into logic. That's exactly what we do. But all the dynamic logic that we have so far do it in a completely different way. They are called dynamic logics, but they are not dynamic logic, at least not in the way we do it. So our approach is we want to say logic is a static thing so far, and we make it now dynamic in a very general way. Okay. Now I want just to show you that we can really have big systems. And this is, you cannot read this, of course, this is the behavior of one customer, that he orders or she orders something, and here it is the order management, his inventory, and some of what is ordered is taken from the supplier, other things from the supplier, and then it's in the warehouse, and then it's the messages given back. So at the end, the order management sends the messages to the warehouse that they should compile something, and then it goes to the freight forwarders, and then it goes to the customers. So it looks cyclic, but it is a partial order. This is one behavior, and this is, let's say, the distributed way of what we in classical informatics have always as sequences. So in automata theory, when you look, you have states, steps, and the behavior is a sequence of something. That makes no sense if the system is really big. It is always a partial order. Something happens in this part of the world, something else, another part of the world, and these things are independent. And this is a partial order. If you don't believe this, then this is exactly the same picture, only written in a different way. So you see the initial part of the customer, and then all the blah, 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 and then the final part of the customer, which we had originally in a circle, something like a circle. Now it's a partial order. And again, the composition operator applies. So you just compose all these components. Okay? Here is the schema. I hope you remember that we had the schematic aspect where we said there may be a set of customers in the set of whatever you have. And while there we have these components here, and also they are composed in exactly the same composition operator. You cannot read this, and I don't expect you can read this. Okay, this looks like a picture, but it is a formal model. This is mathematics. Okay? It's a graphical way of mathematics, and that means you can formally prove something. For instance, you can prove that each order is eventually served. That's what you hope as a client. Or a good delivery, something is delivered only if it has been ordered before. It's also important. And you can prove this because it's mathematics. It looks like a picture, but it is mathematics. And that's very important. You prove this on the level of the model. And when you then implement for instance, this component, then it's correct by construction. And to interplay between customers and computer aspects is proven correct. And that's how we should do it. Okay. Each requested reservation is a way to acknowledge. Each mandated article has goods in the shelf. So if this component says, please pack this and that, it must be guaranteed that the shelves have these objects. And also this you can prove in the model. You can also make a completely different decomposition. You say, well, the business has some paperwork and there are some real items. So we just try to distinguish them, and we can do it in the model. And then you see, this is the paperwork, these are the real items. And the real items come from here, they go to the shelves, they go to the private deliverer, and they are delivered. Also this composition, I forgot, it is a paperwork composed with items. The same composition operator again. Okay, to come to an end slowly, classical informatics has something like modules and composition, and you merge equal interface elements. That is the idea. I think everybody starts this way. If you want to say, oh, I want to model components, you start this way. And then, as I said, you get frustrated because if you start naively, it's not associative. So our suggestion is, yes, do this, but there is not one interface, but two interfaces, the left and the right one. If you are used to it, it's absolutely natural to see the world only full of components with intuitively very clear left and right interface. And we have seen this already. This is the composition of it. Okay. We have static things, data and items, and the symbolic representation of them. Yes, that is what classical informatics also has. But they use symbol chains. They use sequences of letters. This is crazy. This makes no sense, only because two machines need this. There is no reason at all to do this in informatics. Instead, what we should use is signatures and terms over signature, and then we have the notion of an interpretation of concrete system for free. We have the notion of the semantics of the terms for free. So this is the right starting point of informatics, and not sequences of symbols. Okay, for instance, this is a typical problem. And yes, just steal everything from predicate logic and from byte specifications. They have it already, but they did not make it dynamic, and therefore they did not succeed. Dynamics, classical informatics says it's steps, and we say, yes, of course it is steps, but not global steps. Global steps makes no sense. Instead, make local steps, and well, it's of course patronage. Patronage is the theory of local states and steps. So whenever you would try to invent a new theory about locality and say, and the effect is always locally confined, then you inevitably come up with patronage. Okay, this patronage, and to sum up, classical computer science jumps in the right direction. They have very good ideas, but they fall too short. They jump not far enough. And Peter and I started with the Heraclic program, and we adjust this. So it's a research program and a development project, and we cordially invite you to join this. There is so much to be done now, and this is my end of my talk. So do it with Heraclic. Thank you.
Thank you. Questions? Yeah, Christian.
Thank you for the nice talk. I'm not the way to model things, and I think good semantics are really helping us to make stronger, more robust systems. Now comes my but. One thing of internet and communication is that things are working in an end-to-end fashion. So if you're modeling things and staying on the same level of abstraction, things typically tend to become somewhat nicer together, although this is hard enough. But now what happens if you're going down the layers in communication, you encounter soft state, you encounter things like different things are handled differently on different layers, so you have to do all the modeling in your black boxes downwards and still ensure the interface and the schematic is up there. It's this movement, but in a time where you really can communicate.
I agree with you completely. If you would stay always on the same level of abstraction, I would not have dared to show you to show you this. But I thought I have shown you in the example of the business that you can refine one component and refine it several times. We have examples where you have as many steps as you want in one component, and you do not have to refine all the other components around. So it's no problem to have one module and to refine that one module very deeply down until it's the level of implementation, whereas in the rest of the world is just not affected and remains on a very high level. And still the composition functions, because when you refine this,
I'm looking forward to a lot of discussions which will explode the scale of time we have over session. Maybe possibly.
Good questions. We had a discussion on low-code environments, Wolfgang, on Tuesday.
yeah,
And we saw that not only the application logic is relevant, but this is only, let's say, 3 or 5%. The rest is you need to deploy your application, you need to have versioning. In this hierarchy, do you start to think about that?
but that's what we talked, what we told you already, and I don't say it's not true. That is the state of the art, and that is what I really believe is. But to start a project to solve a real world problem, start this way, and then you come to a situation where you start talking about this.
Yeah, sure. That's one answer. The intent is to extend hierarchy finally in the next decade to address all this complex other stuff.
Yeah.
Okay. Further questions? If not, enjoy the dinner and remember that the steering committee is meeting downwards at the bar to discuss next year's edition. See you at 2 o'clock, Johanna? Yes, 2 o'clock.
It's 2 o'clock. The next stop is by.
Take that. See you.
Zweites,